Hello and welcome. I'm Micha. I'm one of the main developers of MS Annika, which is a cross-linking search engine, and I'm going to give you a complete walkthrough of how we can use MS Annika to do cross-link identification from MS spectrometry data. So this tutorial will basically go over all the steps from basically downloading Proteome Discoverer, which you will need for MS Annika, to installing Proteome Discoverer, installing the MS Annika node, which you then will use within Proteome Discoverer, and going through an exemplary workflow with the crosslinker DSSO, where we have some example data that I will use and which should be pretty much applicable to any cross-linking workflow that you're going to use in the future. So the aim of this thing is to go through how we are, basically how you can use MS Annika for cross-link identification. This is not going to cover any of the how the MS Annika algorithm works. If you want to find more out about that, I would recommend to read the two publications that we have about the MS Annika algorithm. And this presentation will also not go over too much cross-linking in general, so it would be advantageous if you have already got some knowledge in this field. Otherwise, I can only also recommend to read through the MS Annika publications. It gives a good introduction to the field, and of course also links to possible other publications where this is covered in more in-depth. If you're already familiar with cross-linking, I will go over the basics of cross-linking very quick at the start of this presentation. Then I will go over the Proteome Discoverer stuff. If you already know all of that, you might just skip ahead. I will link all the chapters that I'm going over here in the video in the description, so you can just skip ahead and go to the relevant parts. The middle part of this video is going to be about the general workflow of MS Annika doing cross-link identification MS2 data. And in the end, we will probably go over some more advanced topics like defining your own crosslinkers in Proteome Discoverer, or how we deal with, for example, MS2, MS3 acquisition. So yes, let's get started. So as an introduction to crosslinking, I always look at it of the way of defining the goal first. What do we want to achieve with cross-linking? And the main goals are basically identifying which kind of proteins interact in my sample, or can I learn something about the structure of the proteins in my sample? And these are the two questions that cross-linking wants to answer. And that works in that way that you have your sample of proteins that you're interested in, and you add a crosslinker, which is a small molecule that covalently links amino acids between either the same protein or between different proteins. As you can see here on the right-hand side, a crosslink can span between two residues within the same protein. In this case, the protein is just called A. Or it can also link between protein A and protein B, so between two different proteins. And what we do afterwards with the sample is a very standard proteomics workflow. You do digestion to break up the protein into smaller parts, usually that is tryptic digestion. And you get these smaller peptides that are now connected by the crosslinker. We call them the alpha and the beta peptide, which are then identified in the mass spectrometer. So what you get out of the mass spec is basically MS1 data, MS2 data, and in some cases, depending on your acquisition workflow, also MS3 data. So in the MS1 spectrum, you get these peaks that still contain the whole crosslink entity, where you have the two peptides crosslinked together. And depending on the crosslinker you use, you either get MS2 spectra that look like this, where you have these very specific doublet peaks that are a certain distance apart. This happens for so-called MS cleavable crosslinkers, where the crosslinker breaks apart during the fragmentation stage, which have this nice property that you can identify the two peptide masses, which makes search a lot easier. On the other hand, you also have non-cleavable crosslinkers, where you also get fragments of both of the peptides in your MS2 spectrum, but you cannot identify the two individual peptide masses anymore, which complicates the search a lot. MS Annika is currently only working for MS cleavable crosslinkers, so for example, DSPU, DSSO, and DSPSO. But we are working currently on also making this work for non-cleavable crosslinkers, so if you're interested in that, stay tuned. MS3 spectra are a special case for MS cleavable crosslinkers. So what you can do is you can isolate these masses from the doublet peaks and do another round of fragmentation and record them in either the orbit trap or the ion trap, and you get basically linear peptide spectra in the MS3 that contain either the alpha or the beta peptide, which we'll talk about later if we are going over MS2, MS3 acquisition in MS Annika. So how does MS Annika basically work? So this is not going to be about the algorithm, but basically what you have is these MS2 or MS3 spectra. And you also have to specify which kind of crosslinker you are using, of course, and some kind of protein database of the estimated proteins in your sample. And MS Annika will use all this information and generate you basically the residues that are cross-linked. And you can use this information then afterwards to do something like this here, which shows, for example, the visualization of prediction of AlphaFold, of the structure of the NSP8, NSP7 complex of the SARS-CoV-2. And with the crosslinks, you basically can validate if this predicted structure, for example, is correct. And because we have a lot of red crosslinks here, so crosslinks that are probably incorrect because the distance between the residues that are crosslinked is too big for actually the crosslinker to fit, it means that this part of the protein that is predicted by AlphaFold to just go in this direction is probably not correct. So this will probably fold in a different way than what AlphaFold predicted. So this would be one of the use cases for using cross-linking is prediction, validation of predictive models, but also for example, you can also use cross-linking data to support your X-ray crystallography structures, or to find out which proteins interact in your sample, which might be important to understand pathways for finding some kind of medication. So, as I already said, you're going to need Proteome Discoverer to use MS Annika, because MS Annika is currently only a plugin for Proteome Discoverer and is not yet out as a standalone application. So what you want to do is basically just Google Proteome Discoverer, and the first link should do it. You will go to the download page of Thermo Fisher Scientific, and you're going to click free demo download. If you don't have a Thermo account yet, you can register for free. I already have one, so I'm just gonna put it in here and log in. And then you go to this, you get this list of software that Thermo provides, and down here you have Proteome Discoverer. We're going to click on that, and usually you would want to use the most recent version for Proteome Discoverer, because that's also the version where we provide the most recent MS Annika for. So we provide MS Annika versions down to Proteome Discoverer 2.3, but not all of them have the same features, as we only implement usually the newest features for the newest versions. So in this case, we're going to download Proteome Discoverer 3.0. And what you want to do is you want to download the installer for the 3.0. And you might also want to download the Proteome Discoverer third-party node, which is here at the bottom, which includes, for example, MS Amanda, which is a database search engine also developed in our lab, which we are going to use for linear peptide identification in our workflow. So I'm also going to grab that. if you don't want to download the third-party nodes, you can also get MS Amanda by going to the website of the IMP in Vienna. So this is one of our partners. So if you go to the address ms.imp.ac.at, you get to the website of the proteomics facility, and there you will find both the website for MS Amanda, which you can open, and the website for MS Annika. So in case you're not downloading the third-party nodes, I would recommend to download the newest MS Amanda version for Proteome Discoverer here. But since we are downloading the third-party nodes, I'm gonna skip that. So for MS Annika, you can either go to this IMP website, where you can download MS Annika for PD 3.0, which is the version that we are going to use, or you can also go to our GitHub page, which is this github.com/hgb-bin-proteomics/MS Annika, where you can also find the newest version of MS Annika here. And this also has a nice change log for you if you want to compare the different MS Annika versions. So for example, our newest version only works for Proteome Discoverer version 3.1, which will come out soon. And we are now going to use MS Annika version 1.14, which is the newest version for Proteome Discoverer version 3.0. And you can check what are the differences between the different versions in case you're concerned about that. So I'm gonna download the newest version for Proteome Discoverer 3.0 now. This will just be a zip folder that contains the installer and the user manual. So first of all, we want to install the Proteome Discoverer. So for that, we just open the installer, which will probably take a while. So this is a big program. You just agree to the license terms. You will need administrative privileges on your PC to install this. And maybe one more thing to mention, so Proteome Discoverer works only on Windows. So we are currently limited to Windows 10 or 11 probably to, yes, so I already have I previously installed this already, so I'm gonna get a warning. If you install it for the first time, you will not get this, but you can just click OK and it should be fine. In the meanwhile, we can just unzip this zip folder. And have a look at maybe the MS Annika manual. So basically what you find in here is all the parameters that you can use in MS Annika and explanations for what exactly they do. But I will cover the most important ones in this video, and most of them you probably will never touch. So if you're interested, you can go through all of that. And if you're specifically looking for an explanation for one of the parameters, this is where you can find it. So let's check how our Proteome Discoverer is doing. So yes, this is still installing. What we can do in the meantime also is on our GitHub page, so this will be on the master branch soon. You can download we have some example workflows, for example, for the SSO, which is for the sole reason that the SSO is the most prominent crosslinker at the moment, most prominent cleavable crosslinker. So what you can do is you can download this example workflow, which we can use later in Proteome Discoverer and don't have to do it manually. So if you're working with DSSO, then just download one of the example workflows from our GitHub page that includes already the MS Annika nodes and the MS Amanda nodes, so you don't have to specify every setting for yourself. So Proteome Discoverer installation is finished. Then we're gonna go and install the third-party nodes, which will install MS Amanda, so the database search engine for linear peptides, and also some other stuff that usually you need a license for. So this is a trial version of, for example, Xlink X and ProSite, which will expire after some time. MS Amanda, on the other hand, is free, so you will always be able to use that no matter what. Even if your license for Proteome Discoverer runs out, you're still able to use MS Amanda and MS Annika in Proteome Discoverer, because both programs are freeware, so you're able to use them without any license. Yes, this should only take another minute, hopefully. Yes. Yes, and that was successful. So the only thing that remains now is also installing MS Annika. For that, you go just into the extracted zip folder and you're gonna click on the MS Annika installer. This will give you a warning because it's, Windows just doesn't recognize the executable, but it's signed by our research institute. So you just click run anyway. Yes, so here you should see that it is by our institute. And you will have to accept the license agreement, and it should automatically set the correct path for your installation, for your Proteome Discoverer installation. So you should not have to change anything. You just click next, yes, and hit install, and it should do everything for you. Then we are going to wait for this process to finish. And finish. And now if we are firing up Proteome Discoverer, hopefully we're going to see MS Annika. And if we see that, then everything worked successfully. If we don't see that, then there's probably an error with setting the correct path. But if that happens, please don't hesitate to reach out to us and we're going to look into that. Usually it should work without any problems. This is, for example, a completely new Windows 11 installation. So if you didn't do any specific modifications, it should work. Yes, so what we are gonna do now after we opened Proteome Discoverer, we are gonna define a new study for where we are gonna do our analysis. I'm just, for the sake of this video, I'm just gonna call this test. And now it creates a new study for us. Then we can immediately check if MS Annika is installed by creating new analysis here in the top. Go to the processing workflow here, click edit, and in the left side we should see the MS Annika detector node, the MS Annika search node, and the MS Annika validator node. So all of them are installed, it seems, so everything worked correctly. So first what we are gonna want to do is we are gonna want to load our protein database that we used for our sample. And so we're gonna go to maintain fasta files, and we are gonna load the So I already did this previously, so I'm going to remove that and show how that works. Yes, so you're going to want to go to add and then add the specific FASTA file that contains all the protein sequences that you're expecting to find in your sample. In this case, this is called high-res, and we're going to load this FASTA file. And in the case for DSSO, which is going to be our example crosslinker for this video, you don't need to do anything else because DSSO is already predefined in Proteome Discoverer in the chemical modifications tab here. So you have here DSSO, the crosslinker itself, and the various monolink forms that DSSO might exhibit. So we are going back to our study here, and then what we have to do is we're gonna have to add our raw files. So in this case, we have our 3 raw files. This is technical replicates. We're all gonna load them into Proteome Discoverer. And once they're here, we're gonna, so maybe from the start again, once you have loaded this, first of all, we're gonna save. And then what you want to click is either Open Analysis Template. So for example, here you can open the template that we downloaded from GitHub. So in this case, this would be a DSSO MS2. And this will already load all the necessary steps, all the necessary nodes that you're gonna use for crosslink identification. So all you have to do is go to input files, mark them, drag them over here into the input file window. And what you still have to do is you're gonna have to specify the parameters that are still empty. So this is the protein database. In this case, it would be the high-res database. And you also have to do this up here in the amend node using the same database. And then you would be good to go. The crosslinker is already set, all the parameters are set. What you might want to change is the MS2 and MS1 tolerance of both the MS Amanda nodes. So here we usually, for the new MS instruments, we usually use 5 ppm MS1 tolerance, 10 ppm MS2 tolerance. So basically, rule of thumb, everything that is Fusion Lumos or newer, just use these. You usually have MS1 resolution of about 60K and MS2 resolution of about 30K, then this is fine. If you're on an older machine or if the resolution is lower, you might want to change this to 10 ppm MS1 tolerance and 20 ppm MS2 tolerance. For example, if you're working on a Q-Executive machine, this would probably suit better. The same goes for the MS Annika detector and the MS Annika search node. But since I'm gonna go over all the nodes now, I'm gonna close this and do this from the start. So what you want to do is you want to click on New Analysis. We can immediately add all our files again here into the input window. And then we click on Edit. So you will see that this workflow window is now completely empty. And we have to drag and drop our nodes that we want to use. So the first node is always going to be the spectrum files node because you're going to want to obviously analyze the spectra. Then you're going to always use the spectrum selector, which will have some parameters that we want to change. So because we are not only dealing with MS1 and MS2 data, but also sometimes with MS3 data, we are going to change this precursor selection to use MSN-1 with parent precursors. So if you're only working with MS2 data, this doesn't matter, but in case you're working with MS3 data, you should change that. And since it doesn't matter if you also use it for MS2 data, it's generally a good idea to just set this to the specified value. Then because crosslink peptides usually exert a higher mass, we're going to change the maximum precursor mass to not 5,000 Dalton, but 10,000 Dalton. And that's about it, what you have to change in the spectrum selector node. After that, you want to have the MS Amanda node, which will take care of identifying linear peptides. So any peptide that is not modified or cross-linked, not modified with the crosslinker or not cross-linked, will be identified by the MS Amanda node. So the first parameter that you have to set again is the protein database. So usually what you also want to specify is additional contaminants database that contains common contaminants that you find in the lab. This fasta that we are using here, so this database already contains some of contaminants, so we're gonna skip this. But it's a good idea to usually, if you not already have it in your fasta database, that you also specify a contaminants database here. For cross-linking, we usually go for a higher number of maximum amount of missed cleavages. So I usually use 4 here, and 5 ppm MS1 tolerance is fine for basically all the current instruments. And for MS2 tolerance, I usually go for 10 ppm. And what you then have to specify are modifications that you're going to expect on your peptides. So for DSSO and for many other cross-linkers, it's usually carbamidomethylation of cysteine, which you're gonna find as a fixed modification, and also oxidation of methionine. This is due to how the sample is usually treated. So we are gonna select oxidation down here, and then you have to select in the second window. You'll always have to specify the specific amino acid that you're considering this for. So in this case, it's methionine, which is the M. And what we're also going to expect is monolink, so cases where the peptide is modified with the crosslinker but doesn't actually crosslink to another peptide. So these are called dead-end links usually. And so the peptide is just modified on one residue with the crosslinker, and the crosslinker then the other end reacts with something in the sample or in the buffer. So which we usually specify for DSSO are the hydrolyzed, the mediated, and the tris form. You can select this down here. Already pre-specified by Proteome Discoverer. So here's the mediated form, and in case you run out of dynamic modification parameters here, you go to this setting over here, show advanced parameters, and it will give you more options to specify the stuff that you need. So I'm gonna specify also the DSSO hydrolyzed version on lysine and the DSSO tris version also on the lysine. So this is about all the settings that you need to specify in MS Amanda. You can additionally increase the maximum peptide length here, for example, to 30 if you're expecting longer peptides also. This really depends on your experiment. If you're looking for any kind of further explanation of the parameters in MS Amanda, please consult the publication of MS Amanda and the webpage, which gives you more details about the specific parameters. After MS Amanda, you need something to validate your results. For the cross-linking workflows, we usually use target decoy validation. So you're gonna use the target decoy PSM validator node, connect that to MS Amanda, and then add a spectrum confidence filter. So basically what happens here, any kind of spectrum that contains a peptide that is identified with high confidence by MS Amanda, then we're gonna filter out this spectrum because we don't want to consider this again in MS Annika to be considered as a cross-linked spectrum. So after that, we're gonna connect this. All the remaining spectra are gonna be forwarded to the MS Annika detector node. So again, you have to specify MS2 tolerance here. So I'm gonna go for 10 ppm again. I usually set the minimum charge to 0 here. which just considers any precursor that doesn't have a charge assigned will be considered as a precursor with charge 1. The rest in the settings you can leave as it is. What's important here now is in the crosslinker settings, you have to specify your crosslinker. So we're gonna use DSSO, and it targets the lysine, so we're gonna specify the lysine here. Then you can specify if your crosslinker reacts to the N-terminal of the peptide. So for DSSO, this is true, so the default is correct. And then you can also specify any additional crosslink doublet distances. So this is one of the more complicated parameters, but for DSSO, what we know is that DSSO fragments in a specific way, so it generates either alkene and thiol as a doublet, or alkene and sulfonic acid as doublets. So to specify all of this, you want to also check here the additional mass difference of roughly 50 Daltons to cover all these cases. But this basically comes down to your crosslinker, what exactly you have to specify here in the crosslinker settings. For DSSO, this is what you want to choose. For most crosslinkers, you don't have to specify additional crosslink doublet distances. You will only have to specify the crosslink modification here. But if you're unsure, it's best to talk to whoever is selling you the crosslinker or whoever designed the crosslinker. What fragments exactly you're going to expect. Another thing you would want to change is usually this top most intense doublets parameter, which I usually set to 3, which basically means if you only find one doublet, so only for one of the 2 peptides, and not the second one, we just take the 3 most intense ones and consider them to be one of the 2 peptides and infer the other peptide by the complementary mass. So after the detector node, what always comes is the MS Annika search node now. So this is pretty similar to the MS Amanda node. Again, you have to specify your fasta database here in the top. You have to specify your digestion parameters, your MS1 and MS2 tolerance again. Here I will again go for 5 and 10 ppm. And miscleavages is already by default 4, so you don't have to change that. Then there is this parameter search approach, so this will depend on your acquisition method. If you're only doing MS2, then you should use MS2. If you're doing also additional MS3, you should change this to MS2, MS3. So MS2 covers basically all MS2 cases, so either just MS2, it covers MS2, MS2, so in case you're doing CID MS2 and ETD MS2, and it also covers stepped HCD MS2, which is the most frequent approach nowadays used. So again, you also, if you're doing an MS research, you have to change this to be the same what you specified in the spectrum selector node, but since we are not doing an MS research, the parameters that are in here currently don't matter. What you're going to change is this parameter called multiplicative penalty for crosslinker with equal sequences. This is usually set to 1. So this means we also want crosslinks where the 2 peptides are of the same sequence. So if the alpha peptide has the same sequence as the beta peptide, we don't want to give any penalty to this crosslink. So again, for the modifications, this is similar to the MS Amanda node, but in this case, we don't specify any cross-linking modifications here. You're gonna just specify the carbon methylation on the cysteine as a fixed modification and the oxidation of the methionine as a variable modification. Oxidation, methionine. Yes, and that's what that is all what you need to set in the MS Annika search node. The rest of the settings are pretty similar to MS Amanda node, because in the background MS Annika uses an instance of MS Amanda to identify the crosslink peptides. What we need after that is some kind of validation of the crosslinks that we find. For that, we are going to use the MS Annika validator node, which does target decoy validation of the crosslink spectrum matches and the found crosslinks. And usually you don't have to change any of the parameters in this node. They can all be left at default. So high confidence FDR, we usually use 1% FDR, and medium confidence 5% FDR. Usually you will let this at the same values that we are using by default here. Then you usually auto layout, so you have a nice layout of your workflow. And the last step we have to do is going to the consensus step. So on the right hand side over here, you have to at least have this kind of MSF files node to generate your output. So that's all what we need for doing an MS Annika search. And since we are having technical triplicates here, what you also want to specify is run by file. So it will do a separate search for each of these files. If all of your raw files are of the same sample, so for example, if they're all from the same chromatography and you're just having separate fractions, so an early and intermediate and a late fraction, and you also all want to search them in the same run, you would untick this at the top. It's by default unticked, but if you want to analyze replicates, you're doing this by file and tick the box over here, and then you go to run. This will submit the job to Proteome Discoverer. And after it's done starting the analysis, it should automatically take you over to the administration window, to the job queue, and you will see that the job started running, and it will give you some kind of percentage for both the processing and the consensus workflow for all of your files. What can happen here is that in the middle of the search, there is a pop-up window that tells you that there is a warning that not all accession IDs are found in target and decoy, in the target and decoy database. If that happens, you can click that away and just ignore it. There is a button that says ignore, just ignore, and the search will run through fine without any errors and problems. We have fixed it in Proteome Discoverer 3.1, but that is currently not out yet. But as soon as that's out, it would be probably a good thing to change to that. But if it happens, it usually happens just to specific kind of fasta files that are formatted in a specific way that the identification or the accession ID is not completely clear and ambiguous. Then it might give you that warning. But as I said, you can just ignore that if it happens, and everything will work fine. If it ran through, it will give you just this. It should mark this job with a green highlight and say completed, and then you can look at your results. I'm gonna not wait for this to run through. I'm gonna open up the study that I did previously with exactly these files and exactly this workflow. And we're going to have a look at how the results look like. So in the end, if the workflows run through successfully, you will have, in the analysis results window, you will have your 3 files or your 3 runs, and you will have your file names in there and the execution state, which should say completed or completed with warnings. In case any of the spectra that you're trying to read from the raw file are incomplete, which again does not affect the search. It's just something to be aware of. In our case, our raw files all were fine, so there were no warnings, and our jobs completed successfully. And what you get, you double click on this result file, and then you will basically see all the results. So usually by default, it opens up the proteins window, and then you can see the coverage of all the proteins. So what we are basically seeing that most of our proteins in our sample were the androgen receptor of the mouse, which we also will see in the crosslinking tab afterwards, that most of our crosslinks are within the androgen receptor in the mouse. The specific results of MS Annika, a good overview is always the crosslink summary, which will tell you how many high confidence crosslinks or crosslinks that fall within the 1% FDR threshold are found, which how many medium confidence crosslinks are found. So these are crosslinks that fall within the 5% FDR threshold, and the total number of crosslinks found that are not validated. So in our case, it's roughly 100, or it's exactly 185 crosslinks that have high confidence, which we might want to look further into. So you can then find the crosslinks in the tab crosslinks. So this will just show you all the crosslinks without validation. If you want to just look at high confidence crosslinks, so crosslinks that fall within the 1% FDR threshold, you go to the symbol over here where you can filter, and you're gonna add property confidence is equal to high, which will only give you 1% FDR crosslinks. And usually you also don't want to display any decoy crosslinks, so we're gonna specify decoy is false, and you get your 185, in this case 184, because one of the crosslinks was a decoy, so it was filtered out. 184 crosslinks that fall within the 1% estimated FDR threshold. And you can already see that most of these are from the androgen receptor of the mouse. And every crosslink is basically a grouping of one or more crosslink spectrum matches, this is called, where a crosslink is associated with a specific spectrum. So if you click on this crosslink and then show associated tables, you can also see the crosslink spectrum matches that this crosslink is associated with. So we can see that we identified this crosslink in the scan number 2438 and in the scan number 3058. And you can find all the crosslink spectrum matches also in the CSM table over here. So you could also filter this again for confidence the same way we did with the crosslinks, if you're interested in that. Another table that we might be interested in is the peptide spectrum matches. So here we find both information from MS Annika and MS Amanda. So you will find, for example, monolinks in here. So you find basically every peptide that was identified in which spectrum it was identified in. That's basically the standard workflow using MS Annika for crosslink identification. The most important output usually is the crosslink table and the CSMs table. Again, usually filtered for confidence equal to high, because we are usually only interested in 1% FDR crosslinks. With this information, you then can use this to, for example, map crosslinks to a structure, look at the specific crosslinks where they are within the protein sequence. What you would have to do for that is going to File and Export. So I'm gonna have this already prepared for, I think, this file. In this case, I'm filtering, if this loads. So I'm filtering basically only for crosslinks where of the androgen receptor of the mouse. So accession A has to be this accession ID, and accession B also has to be this accession ID. which gives me in total then 53 crosslinks where this is true. And what I want to do is I want to export this to a Microsoft Excel file. And here it lets me specify which table I want to export, and this is already correct. So I want to export the crosslinks table. I think by default it's proteins, so you have to change that to crosslinks, and then you specify the path that you want to export it to. I'm gonna specify just going save this in documents. Then I'm gonna click export, and it should create an Excel file in the specified path. So if I now go to documents, I should have this Excel file in here that contains all the crosslinks that are within the 1% FDR threshold as specified here. No decoy crosslinks, and both accessions are of the androgen receptor of the mouse. And that's basically the part in Proteome Discoverer. And what you then can do is we have some exporter scripts that let you export these results to different downstream crosslink and analysis tools. So you want to go to the GitHub address of our research lab / MS Annika _exporters. And these are basically all Python based. So if you have Python installed, you can run them as Python scripts. If you don't have Python installed, we also have Windows binaries in here. So you don't need to install Python for that. So the tools that we currently support is exporting to Xinet and xiVIEW. Both are web-based tools by Yuri Rapsilber's lab. And we also have exporting options to PyXlink Viewer, which is a plugin in PyMol where you can visualize crosslinks in the 3D structure of a protein. The same also for Chimera X using the plugin XMES. And also we have an exporter for the predicted alignment error viewer, which is especially useful if you're having some kind of predicted structure from AlphaFold and you want to validate that. With cross-linking data, you can use this PAA viewer to load your structure and load your crosslinks, and then you can see how that matches up, and it gives you some nice summary statistics about it. So I'm gonna show specifically how we're going to do this with xiVIEW, because it's a very mighty tool and gives you a lot of options, both for 2D visualization, so visualizing the crosslink on the sequence of the protein, but also 3D visualization using a PDB structure to map the crosslinks to a 3D structure and see how that looks like. So I'm gonna just use the Windows binary. I did not install Python yet. So it works exactly the same. Basically, the commands are exactly the same. But for Python, of course, you have to specify the command line, the Python interpreter before you call this the Python script. So I'm gonna download the xiVIEW exporter executable here. And yes, again, you're getting a false positive warning, so you just specify you want to keep this because it thinks it's a virus. But again, so all the code is open source here. If you don't trust it, compile it yourself. What we are then going to need to do is, as specified here, we're going to look at the usage of the exporter. So what you have to specify is first the MS Annika result file. So this will be our Excel file that we exported. Then you have to specify the fasta file containing the sequence of the protein that you want to look at. And optionally, you can specify if you want to ignore a specific protein and an output path or output file name. So first, what we're gonna do, I'm gonna copy the fasta file that we had to our documents folder and copy our exporter to our documents folder. And we're going to modify this fasta file now because it now contains all of the sequences, but we only want to have the androgen receptor in there because we're only interested at the androgen receptor. So I'm gonna copy this entry, remove all the rest. And all the exporters have a very specific requirement, and that is that the fasta file is in the UniProt format. I think it says it's somewhere over here. Yes, fasta requirements. So the fasta headers need to follow the UniProt KP standard formatting as described here in this link, which means that all the entries should be specified as the DP name, then the pipe symbol, then the accession number, then the pipe symbol, and then any kind of other description of the entry, and then the entry. So in this case, our fasta file does not follow this specific formatting, so I'm just gonna change that. I'm gonna put the okay, it doesn't let me do the pipe symbol on my keyboard. It seems like nope. If you're not, you just go to Google for the pipe symbol, and we are just gonna copy and paste this into our fasta file. And this should now be in the correct format, so we should be able to read this with our exporter script without problems. So what we're gonna do, we're gonna open a command line window in here. That is in Windows 10 and 11. You can just type CMD into the path here. Should open up a command line window. You specify the name of the exporter, then your result file, which is in this case our Excel file, and then we have this parameter fasta, which is our high-res. And this will now give me an error when it runs through, because our fasta file does not contain this excuse me, androgen receptor of the red sequence. So we additionally need to specify to the exporter that we want to ignore this because we don't want to map this. So we're going to specify ignore, and then we just specify the exact name of the error. And this should give us the files that we need for xiVIEW. So now you see this ran through correctly without errors. So what we're gonna do, we're going over to Google xiVIEW, and you're going to get to this web page. And what you will need to do in case you don't have an account already, you create an account. Again, this is for free. I already have an account, so I'm just gonna sign in with my credentials. And you will be presented with this window. And what you will do is go to upload data and choose your files. So I will go to the documents folder. The two files that are generated are the CSV file and our new fasta file that we're going to use for xiVIEW. We open this, and then you click submit data. Then your data is processed, and you will end up with this view. So here you have the androgen receptor of the mouse, the sequence basically laid out in this one string, and you see exactly which residues are cross-linked with each other. So you will see this position lysine in position 45 is linked with the lysine in position 365. And this crosslink has a score of 231. So this is a pretty high score. You can basically go through all of these crosslinks. It highlights them for you if you hover over them and see some additional information. Now, another thing that you can do is you can also upload a PDB file to visualize this in a 3D structure. So in this case, we have to find the specific PDB file first. So I'm going to look at our fasta file. We have some identifier in here that we can Google. So usually you already know about the proteins that you're analyzing beforehand, so you can look them up on the PDB. In this case, I got these raw files without very much information, so I'm just gonna have to make use of the information that I have. I'm gonna Google the specific identifier. It links me to this site of the androgen receptor. And luckily we have a protein 3D structure that is associated with this. So we're going to go to the PDB over here, download this 3D structure in PDB format. And then we're going to upload this into xiVIEW. So we could also just specify the 4-letter PDB code here, but we already downloaded the PDB, so let's just do this. And it will tell you success, so one sequence map between the search and the PDB file, which is exactly our androgen receptor sequence. And if you go to views now, you can select the 3D view, and you will see the 3D structure of the protein with our crosslinks mapped to the specific residues. Again, you can hover over these crosslinks and it will tell you how long are they, which residues are crosslinked, and which score do the crosslinks have. So usually for DSSO, so this also depends on your crosslinker, but for DSSO, we usually use a threshold of 27 to 35 angstroms of the maximum distance that a crosslinker can cover. So depending on which threshold you exactly use, you would consider this a true or a false crosslink, or maybe even, or if you go it the other way around, you would consider that maybe this is not the correct confirmation of the protein in your sample. Because this is almost 31 angstroms long. So if you consider 35 angstroms to be your limit, which is possible with DSO, you would consider this to be a correct one. If you're more conservative and consider 27 angstroms as your limit for the crosslinker, you would consider this to be false. So this means either the identification is false by the search engine, or the structure that you used here is not correct in the sense that it is not in the confirmation that the protein is in your sample. You can click through all of these crosslinks, specify them individually, look at them individually, and see how to interpret all this kind of results. Yes, that's basically the 3D viewer. You can also use get something like this, of course, in PyMol and in Chimera X, with some additional coloring options that you can color the crosslinks depending on the length of the crosslink, which is usually very helpful to see immediately which of these crosslinks are plausible, which of them are not. Unfortunately, I have not found out if that is also possible in xiVIEW, but it's definitely a thing that you can do in both PyMol and in Chimera X, which we also have exporters to. That's basically it for some basic introduction to MS Annika. So to cover more advanced topics, I would now go over to cover the case where what happens if your crosslinker is not already defined in Proteome Discoverer. So in the case that your lab is synthesizing a new crosslinker and you have to do some search, you will want to go to the administration menu, go to chemical modifications, and you want to add your crosslinker here. So you're going to press the little plus sign on the top left. You have to, usually position is any, basically you have to specify a name for the crosslinker, an abbreviation. You have to specify the monoisotopic delta mass of the crosslinker modification and the average mass of the crosslinking modification. You then, the substitution window covers the exact atomic composition of the crosslinker. So example, maybe look at the DSSO, you get the exact atomic composition of DSSO here. So you specify the atom and the count within brackets. Then what you have to specify is the target amino acids that this crosslinker can react with. For DSSO, this is usually lysine, as we specified here. Sometimes you would also want to consider ST and Y also as potential reactive sites for the crosslinker, specifically for NHS ester crosslinkers like DSSO. You would want to specify ST and Y also additionally to K, but usually lysine covers 80 to 90%, if I'm correctly, of all crosslinks. So the difference between specifying K or K, ST, and Y is usually not that big. Then the second tab that is very important is, of course, the crosslinking tab, where you have to specify the crosslinking fragments. So for the case of cleavable crosslinkers, so first of all, you have to specify here that you're creating a crosslinker. So in this case, it's a cleavable crosslinker where you have to specify the 2 fragments, or in case your crosslinker has more than 2 fragments, you basically specify the light and the next heavier one in here. So in this case, the light fragment of DSSO is the alkene fragment, and the heavier fragment is the thiol fragment, the next heavier one. And so you specify both the fragment names and the exact atomic composition of the fragments that you would expect on your peptides. And then you have to specify the 2 that they are connected, basically. You also have to specify again the target amino acids that they react with. This is again lysine, and this can only be values that you already specified in here. And what you also might to consider is diagnostic ions. So if you have any kind of diagnostic ions that you find in your cross-linked spectra, you want to specify them here. So MS Annika can use these ions to identify spectra that for sure contain cross-linked peptides. Another tab that is usually only important if your crosslinker has more than 2 fragments is the neutral losses tab. So DSSO only has these 2 fragments with the addition of a sulfonic acid fragment, but the sulfonic acid fragment just differs from the thiol fragment by having an additional H2O, which you don't necessarily have to specify because H2O usually is covered within the neutral losses. But if there is any other kind of fragments, you usually want to specify them in the neutral losses tab. So any other fragment than specified in here should be specified in the neutral losses. But this is usually only the case, again, for very specific crosslinkers. If they fragment with more than 2 possible fragments, which is honestly not very desirable, but it happens. Usually it is enough to go for the general tab, specify the exact crosslinker masses here, and specify the 2 fragments in here. And optionally also specify some diagnostic ions if you find them. So this is about defining a new crosslinker in Proteome Discoverer. What you also should then do is, of course, defining the monolink forms of them. So usually you have an mediated form if it reacts with ammonia, or if it's hydrolyzed, then you should also specify the hydrolyzed form. For these ones, it's not important you don't need to specify any cross-linking stuff, because this is only considered for the monolink, which is not important for identifying doublets. And also the tris buffer form usually is also specified if you have that. If you have non-cleavable ones, the process is of course much easier, because you don't have to specify any kind of fragments here. You just go to non-cleavable crosslink, and it will you only have to select which kind of amino acids do the 2 ends of the crosslinker react to. But again, at the moment, unfortunately, MS Annika is only able to deal with cleavable crosslinkers, but in the future, we aim to also incorporate non-cleavable ones, and that might come in handy then. Another topic that I'm going to cover in the last step here is what happens if you are having MS3 spectra. So we are gonna look at the analysis workflow here again. So in case you're doing MS2, MS3 acquisition, so recording an MS3 spectrum for every doublet peak in your MS2. There is of course, in the MS Annika search node, you have to specify here the search approach to MS2, MS3. And then you will want to go, what you have to take care of is that this precursor selection parameter exactly matches up to the spectrum selector parameter with the same name. So in both cases here, we used MSN-1 with parent precursor. If that doesn't match up, MS Annika will probably give you a warning and not run through, and the search will terminate. So basically make sure that these 2 parameters match up. And additionally to our MS1 and MS2 tolerance now, we have this parameter MS3 tolerance. So this is the fragment ion tolerance for MS3 spectra. And this is going largely to depend on where your MS3 is recorded. If your MS3 is recorded in the ion trap, you usually use a very high tolerance here of, for example, 0.5 Dalton, which is the usual tolerance for ion trap spectra, no matter the instrument. If you're recording MS3 spectra in the orbit trap, means basically that the MS3 spectra are usually of high resolution, so you either use 10 ppm. If your MS3 resolution is, I would say, 15,000 to 30,000, you definitely can get away with 10 ppm to 20 ppm if it's a bit lower. So for orbit trap MS3 spectra, try 10 ppm. If that doesn't yield you a lot, try 20 ppm. These are basically the most crucial things for MS2 and MS3 acquisition. All the other parameters are basically staying the same. because they are not depending on which acquisition method you're using. So that's about it for MS Annika. If you're having any questions, if you're running into any troubles, or if you're having any feature requests, please don't hesitate to reach out to us. I think our mail addresses, so either you're dropping us a mail, where are they displayed? Yes. So my address is micha.birklbauer at fh-hagenberg.at. They're all here in the contact section of the MS Annika webpage. You either can contact us directly by mail, or you can also open up an issue on GitHub. I also check that regularly. So if you have any questions, any kind of feedback, if something doesn't work as expected, if you're encountering a bug or an error, or also in case if you have a feature request, please don't hesitate to reach out to us. We will look into it and get back to you as soon as possible. So that's about it for MS Annika. I hope this was a helpful introduction to how to use MS Annika for cross-link identification. And we hope that you're considering MS Annika to use if you're doing cross-link identification. That's it for me.